Today, we are reviewing a paper titled GPS-Gaussian. Let's dive into what the paper covers. Initially, it introduces the term generalizable, implying a model that is trained on multiple entities and then able to rapidly render new entities as they are introduced. This process is often described using generalizable models and involves pixel-wise 3D Gaussian splatting. In essence, this technique constructs a 3D Gaussian on a pixel basis. Moreover, from the perspective of real-time human rendering, this method enables fast rendering and novel view synthesis. In the overview, the application being developed is first described. The training employs a pixel-wise 3D Gaussian estimation model. The dataset is set up with a person at the center, surrounded by 8 cameras placed at 45-degree angles. These captured images become the training and test datasets, sourced from Twindom and Thuman, and are structured in a specific ratio for training and testing. During the testing phase, images are synthesized from new views without foreseen optimization. Below, you can see 2 images, the left 2 are input images, and the right one represents a novel view image. For better visibility, I've drawn lines to highlight the frontal view, which I refer to as the novel view pose. The image on the right corresponds to this frontal view. To render this view, inputs from the 2 nearest cameras are used. The first camera's pose can be seen in the illustration, positioned accordingly, while the second camera version captures the side view. These 2 images are combined to synthesize what you see. The study achieved rendering at 25 FPS on an RTX 3090, using images with a resolution of 1024 by 1224. The paper presents research results involving various angles of novel view image synthesis. The overall structure is outlined as follows. From 8 potential images, the 2 most similar to the actual novel view pose are selected. These selected views are processed through a CNN network and an MLP to estimate depth. This depth estimation module processes the derived depth information for each pixel, which, along with the pixel's color values, is used to determine the Gaussian parameters. As shown in the right image, a person is composed of 3D Gaussians. Each 3D Gaussian splatting parameter includes location, color, rotation, scale, and opacity. These 5 values form individual 3D Gaussians, collectively rendering the image through 3D Gaussian splatting rendering. This process effectively represents images using these techniques. The remaining parameters, like rotation, scale, and opacity, are extracted through a second network called pixel-wise Gaussian parameter prediction, which utilizes a UNet and 3 headers to derive these values. We will look in detail at how these depth values are directly utilized for novel view synthesis. Here, depth estimation is conducted using 2 camera parameters provided. If one image is captured from 2 different poses, a disparity value is calculated. This disparity is used to estimate depth, creating a model that can accurately extract depth based on the position and pose of the camera. This premise is crucial, the point in one image and where it appears in another image. Thus, the model estimating this point becomes a disparity estimation model. Hence, disparity estimation approaches the depth estimation equivalently using the RAFT algorithm, part of the optical flow algorithm family. The formula below shows the disparity function, where RAFT infers u, v, and xy values. However, here the formula is fixed in a horizontal direction only, allowing faster estimation. This form of RAFT, based on an optical flow algorithm, utilizes a transformer-based recurrent method, as inferred from the title. After extracting features from 2 images, they are input into a recurrent network to derive optical flow, but here it is used to estimate depth based on the movement distance of a single pixel. Next, pixel-wise Gaussian parameter prediction is used, allowing for estimation through a depth map. This input is processed using an encoder and decoder, specifically a UNet structure, to estimate 3 parameters: rotation, scale, and opacity. The backbone shared in this process passes through 3 different headers to obtain these values. The inputs include encoded values for the image and depth, which are then used to form the backbone of the network. It's worth mentioning that this is a pixel-based process where each pixel creates a Gaussian inside. Looking further into the network, the depth estimation is located at the top, which corresponds to the RAF network, transferring features from the image encoder to the UNet for color information processing. This UNet is a module for estimating 3 Gaussian parameters. Intermediate features from RAF are input into the UNet along with the depth map. Here, 5 parameters are trained jointly and updated simultaneously using a rendering method to calculate the loss, which I will show first. This illustration is from 3D Gaussian splatting, where a 3D Gaussian is first created per pixel and then projected using a rasterizer to create the image. Only this part is used for rendering. The difference between this rendered image and the GT-RGB image is calculated to update the loss. This section describes the rendering loss, including L1 loss, to which SSIM loss is added at a certain ratio for calculation. Depth information also calculates disparity loss using GT values to assess the difference with the predicted depth. These losses are combined to simultaneously train 2 networks. The results compare 5 different studies. In the case of 3D Gaussian splatting, it is not just unrenderable from 8 views but also because it is not a generalizable model, which is indicated by the absence of FPS in the comparison. The other models are generalizable and thus show numerical values. The mentioned paper displays the fastest performance at 25 frames with high PSNR, SIM, and LPIPS values. The training time for other papers was not verified, but this paper reports 15 hours on a 3090. The images below are described starting with the first as GT, followed by ours, ENRF, IBRNet, and Florin, showcasing the high quality of the GPS-Gaussian. Next, the test results show exceptionally high quality. A particularly interesting point for me was the Gaussian splatting. It's fascinating how even with limited input, it can achieve quite high quality. In the ablation studies, instead of 8 cameras, tests were conducted with 6 cameras. The results below are from when there was no joint training and no depth encoding. It is noticeable that the performance significantly drops when joint training is absent. This concludes the presentation. Thank you.